Today we're going to talk about the hypothesis testings with examples. So here we go.
In recent years, the mean age of all college students in City X has been 23. This year, a random sample of 42 students revealed a mean age of 23.8. Suppose their ages are normally distributed with a population standard deviation of 2.4. Can we infer at alpha equals 0.05 that the population mean age has changed? Since we're testing if the population mean age has changed from 23, the alternate hypothesis would be that the mean is not equal to 23, and the null hypothesis will be that the population mean equals 23. The significance level alpha is 0.05, or 95% confidence. Since this is a two-tailed test, the rejection region will be in both tails of the distribution. So we divide alpha by 2 to have 0.025 in each tail. Next, we find the critical values. That is, the values that separate the rejection region from the non-rejection region. For single population mean tests, we either conduct a z-test or a t-test. If the population standard deviation sigma is known, a z-test is employed, and if the population standard deviation is unknown, a t-test is used. In some courses, however, due to the central limit theorem, whenever the sample size is large, and some textbooks say when n is at least 30, apply the z-test, whether the population standard deviation is known or not. The onus is on you to check what obtains in your course. For this example, we will conduct a z-test because the population standard deviation sigma is given. We now find z critical values that define the critical or rejection region using the standard normal table. The two commonly used z-tables are the cumulative less than tables with negative and positive values, and the cumulative from mean tables. These pictures are usually displayed at the top of the respective tables. To find the critical value on the cumulative less than table on the negative side, since the area in the left tail is 0.025, we then search for the closest value to 0.025 in the body of the table. We actually have 0.025 here, corresponding to a z-score of negative 1.96. And because of symmetry, the positive score is also 1.96. In the mean to z table, the entries represent the areas from 0 to z, shaded here. And because we have 0.025 in the tails, and the area on either side of the mean is 0.5, then the area from 0 to z is 0.5 minus 0.025, which is 0.475. We then search for the closest to 0.475 in the table, and we have the actual value here, corresponding to a z-score of 1.96. And because of symmetry, the z-score on the left will be negative 1.96. Sometimes we can also use the student t distribution table to find the z critical value. When you scroll to the bottom of most t tables, you either find infinity or z on the last row here. This is because the t distribution approaches the z distribution as the sample size becomes very large. So these are actually z critical values. And if you check under 0.025 in one tail or 0.05 in two tails, you will see that the corresponding critical value here is 1.96. So back to the hypothesis test. Based on the critical values found in the tables, we can set the decision rule as follows. Reject the null hypothesis if the test statistic, based on this formula, is less than negative 1.96 or if it is greater than positive 1.96. So using the sample mean, population standard deviation, and the sample size, we calculate the test statistic as 2.16. And now it's decision time. Since z equals 2.16 is greater than 1.96, we reject the null hypothesis. Because the null hypothesis, which states that the mean age is equal to 23, has been rejected, we then have to support the alternative that states that the mean age has changed. So we say we have enough evidence to conclude that the mean age has changed at alpha equals 0.05. Now suppose we conduct this same test at 2% significance level. The null and alternative hypotheses are still the same. The significance level alpha is 0.02. Dividing alpha into the two tails, we have 0.01 in each tail. Looking this up in the t-table, under 0.01, one tail, or 0.022 tails, we see that the critical value is 2.326, which we can round to 2.33. So we reject the null hypothesis if the test statistic is less than negative 2.33 or if it is greater than positive 2.33. The test statistic remains 2.16, which does not fall into the rejection region. We therefore fail to reject the null hypothesis. Consequently, we cannot support the alternative. Therefore, at alpha equals 0.02, there is not enough evidence to infer that the mean age has changed. And that concludes this tutorial. Thanks for watching.